Okay, so let's move on to an introduction of limits. And limit is a very important concept in calculus, so we're going to get started on that. In this particular PowerPoint presentation, you will understand what calculus is and how it compares with pre-calculus. Calculus, pre-calculus. Pre-calculus is a preparation course for calculus. And secondly, you will understand that the tangent line problem is basic to calculus. Tangent line problem. Also, you will understand that area problem is also a fundamental concept in calculus. Area problem. So, what is calculus? It's a very good question. You should think about this. So calculus actually is mathematics changes, meaning it captures motion. For instance, calculus is the mathematics of velocity, acceleration, tangent line, slopes, areas, volumes, arc lengths, centroids, curvatures, and a variety of other concepts. This enables scientists, engineers, and economists to model real-life situations. So this is a key implication, right? You can use calculus to model the real-life situations. However, pre-calculus is a prep course, as I mentioned earlier, deals with velocity, acceleration, tangent line, slope, and so on. But there's a fundamental difference between pre-calculus and calculus. Pre-calculus is more static, and calculus is more dynamic. So that's the fundamental difference between the pre-calculus and calculus. First of all, let's take a look at some examples. So an object traveling at a constant velocity could be analyzed with pre-calculus. To analyze the velocity of an accelerating object, you need calculus. Okay. The slope of line could be analyzed using pre-calculus, but in order to analyze the slope of curve, then you will need calculus. The curvature of a circle is constant and could be analyzed with pre-calculus. To analyze the variable curvature of general curve, then you need calculus. The area of a rectangle could be analyzed with pre-calculus, but in order to analyze the area and the general curve, then you need calculus. So one way to understand what calculus is the limit. So the first stage is you need to understand the pre-calculus mathematics, such as the slope of a line or the area of a rectangle. The second stage is the limit process. And the third stage is the new calculus formulation, such as derivative or integral. So start with pre-calculus as a foundation. Then you move on to limit process. Then after that, you come up with the calculus. This flowchart actually gives you a very good idea the relationship between pre-calculus, limit, and calculus. So this is basically a comparison between left column with pre-calculus, right column is the calculus. Given any x value, let's say x equals c, you'll be able to find the y value, which is f of x or f of c, right, in this case. And in the calculus, we will learn to find the limit of f of x when x approaches c. From left and the right hand side. And the pre-calculus, you will learn the slope of the line. Slope equals the change of y or change of x. So this is the tangent of this particular angle. Right? Let's say theta. And here in calculus, we'll be able to calculate the slope of curve at this particular point. Right? On a particular part of the curve. In pre-calculus, we already know the secant line to the curve, which is 2 point, give us a slope, right? Slope will determine the secant line. Here, in calculus, you learn the tangent line. Tangent line to a curve is a line passing through the point, and it's going to be perpendicular to this. It's going to be perpendicular to the point. And in pre-calculus, you already know how to calculate the average rate of change between two time t at A and time t at B. And average rate is speed or velocity, right? And in a calculus course, you'll be able to calculate instantaneous rate of change at any particular moment time t equals c. At any time t c. Okay. Now just some example about difference between the pre-calculus and calculus. So there are more examples, right? So in terms of curvature at a circle, that's still pre-calculus stuff. Pre-calculus. This is calculus. And using calculus, you'll be able to find the curvature of a particular curve is compared to a circle in pre-calculus. And you will be able to analyze the maximum height in a given interval, let's say from interval AB, to find the maximum or minimum height on a curve on a particular interval. Also, a tangent plane to a surface, that's a key feature of the calculus, and direction of motion along a curve, which is applied in physics very frequently. It's like a fundamental concept in physics. Without calculus, you can only calculate the area of a rectangle. With calculus, you will be able to find the area under a curve. This particular area with a curve. Right? Without calculus, you can find the work done by a constant force. However, with the help of calculus, you'll be able to find work done by a variable force, which is a lot more complicated. And without calculus, you can find the center of the rectangle. With the integral calculus, you'll be able to find the center of a region, which is a lot more complex. And without calculus, you can find the length of this line segment, just like that one, using distance formula, given the coordinates of the 2 points. With the help of calculus, you can find the length of the arc. Without calculus, we can find that in the pre-calculus, you can find the surface area of a cylinder. But in calculus, you learn how to find the surface area of a solid of revolution, which is in calculus 2 in our school. And in pre-calculus, you can find the mass of a solid of a constant density. And in calculus, you'll be able to find the mass of a solid of variable density. In pre-calculus, you can find the volume of a rectangular solid. In calculus, you can find the volume of a region under a surface. In pre-calculus, you can find the sum of the finite number of terms. And in a calculus, you'll be able to find the sum of the infinite number of terms. So that's a major difference between the pre-calculus and calculus. So next thing, let's take a look at the tangent line problem, which is a very crucial topic in calculus. So notion of limit is fundamental to the study of calculus. A following brief description of 2 classical problems, tangent line problem and the area problem, to give you some idea of the way limits are used in calculus. In the tangent line problem, you are given a function f of x. In this case, this is our function. And a point P, in this case, point P is right here. On this graph, and asked to find the equation of tangent line to the graph at a point P, as shown in figure 1. The key thing is tangent line also is a line. So in order to find a line, you need 2 things, right? Slope and a y-intercept. So whatever you learn in the algebra course, you can apply here with a layer of limit. So this is a typical demonstration of tangent line at a point P. Finding the tangent line at a point P is equivalent to find the slope of tangent line at a P. As I mentioned, slope is always one of the most fundamental term related to any line. And you can approximate slope by using a line through the point of tangency and the second point on the curve. I'll show you this is point P. And let's say we have another point somewhere here. So the slope at that point we're using change of y and over change of x. Right? So in this case, the slope is equal to f of c plus delta x minus f of c over delta of x. Okay, this is change of x, that's change of y. And such a line, right, is called a secant line. And secant line is a very important concept with respect to tangent line. So as I mentioned in the previous slide, secant line slope equals, let's say the second point is just first point, this x value is c, and second point, the x value is c plus delta x. This is delta x. So that's at this point, the x coordinate is c plus delta x. And then the y value at this point is going to be f of c plus delta x, and y value at this point is going to be f of c, okay, which is the same as that. This distance is the same thing as that. This is f of c, and that's why this is f of c. That's why the total is f of c. So the change of y is f of c plus delta x minus f of c. Change of x, just delta of x. Okay. That's why we end up with this secant line formula. F of c plus delta x minus f of c over delta of x, using fundamental slope change of y over change of x. Delta y over delta x. That's how we come up with the slope of secant line. So as you can see, right, you can come up with the infinitely many secant line, but in order to make the secant line as close to the tangent line, so eventually we're going to move the point as close, very, very close to that point P. So right here. To guarantee, so in this case, we come up with the limit process. Just keep going this way until your point gets infinitely close to P. So this is first time using limit to interpret the tangent line, the slope of tangent line at a particular point P. Okay. So the tangent line is actually said to be the limit of the slope of all the secant lines, and then we have infinitely many secant lines. So this is the first time we're using limit to define the tangent line. The key thing is just moving point Q as close as possible to point P. This is point Q. Eventually you come infinitely close to point P. And that's how you determine the equation of tangent line. The second applied area is called area problems. So second classical problem in calculus is finding area of a plane region that is bounded by graphs of functions. And this problem can also be solved with a limit process. So again, we're going to use limit process to interpret the area problem. In this case, the limit process is applied to the area of the rectangle to find the area of the general region. Okay, for example, we have a curve y came from y equals f of x. So this is our curve. We will figure out the region, the area bounded by these two x values, x equals a, x equals b. So we basically want to find the shaded regions in pink. And using the calculus knowledge we're going to learn later, we'll be able to find the area bounded by any graphs of any functions. Okay? This case is bounded by this x-axis, x equals a, x equals b, and a function f of x for this particular region. In this case, a lot of mathematicians try to use different methods to approximate the area under the curve. One of the methods using the rectangular regions. They separate the shaded region in pink into like different amount of rectangular regions, rectangular shape. In this case, first graph gives us this first rectangle, second rectangle, third one, fourth one. And when we combine all the areas of the four rectangular regions, then that's going to be the approximate area. Bounded by x equals to a and x equals to b. Okay. And the second graph, as you can see, we turn into 8 different areas. Think about this. Which graph gives us a better approximation? Is it graph A or graph B? The answer is graph B. This graph gives us better approximation because the more area we have, the more rectangular regions we have, the better it is, better approximation is. So again, this is just a way to approximate the area under the curve. Although the answer is not exact, but it's quite accurate, right? When you have sufficient amount of rectangular regions. As you increase the number of rectangles, the approximation tends to become better because the amount of area missed by the rectangular decreases. So this is the reason why the more rectangular region is better off. The goal is to determine the limit of the sum of the areas of rectangles as the number of rectangles increases without bound. So again, we're using limit, right? Limit process to approximate the area under the curve. So this is what the essence of calculus